continue the story, and now it will be, back home. Here you will spend 2 years at least of your life, or more, or less, depends on how you perform. I'll keep you busy only for 3 weeks with classes, and then you will have the lab. And today we'll continue the discussion on, kind of fundamentals, and we'll return where we stopped, which was the performance. Then, if I have a number of processors or a number of computers, what I would like to know is which one is better. And performance, it's a measure of being better. Now, what do we understand by performance did change in time. In the early days of computation, performance meant essentially time. Then, the shorter it took to a computer to execute the program, the better the computer was. Due to the evolution of technology, but also of the applications, things changed slightly. And today, they are very much different. Slowly but surely, energy became more and more important. And in the latest time, good morning. Then when you enter a room, what do you say?
Good morning.
Okay. See? This is a traditional attitude. You should not do that, right? It's old-fashioned.
Good morning.
No, but there is a reason of not doing that. Just not to disturb the people. If you come late, you get close. You are not afraid, right? Yeah. I don't bite you, even though some of you are very high. You want to have a view on your colleagues to see how they follow the course, right? I do understand you. When I was a student, I was sitting only up there. It's fun, You see everybody, you see what they are doing. If they play with the telephone, they read email, they sleep, they eat, whatever. Okay, essentially the majority of you should try to listen to what I'm saying. Then, lately technology has a fundamental problem with reliability. And then there is a migration of performance being measured in terms of time towards performance being measured in energy and being measured in error rate. Then we have some kind of combination. While for performance in time, things are very well formalized, for performance in energy and for performance in error rate, things are not that clear. The community is trying to solve them, to understand them in a better way, but there is still a lot of work to be done in order to get to the same kind of formalism and understanding. If you are familiar with logic design, and I assume you are, you know that it's very easy to understand the performance, the delay of a circuit, and it's not that obvious to understand how much energy the circuit will consume. By visual inspection, if I see a circuit in, let's say, transistor level, may be a bit more complicated to understand, but gate level, I'll tell you immediately if A is better than B. If I know a bit about technology also. In energy and in error rate, things are not that simple. Now, we'll stick with the definition of performance in terms of execution time, and as I said, the shorter the execution time, the better. I hate this room because I am in a very awkward situation. I would like to see the slides also, not to deviate too much from them, but I don't like to stay there. And you have fantastic view from there, but if I move up there, you won't see me. Then it's a catch-22. Do you know what catch-22 is? Never heard about catch-22? Okay, so it's a movie. Essentially, it's a vicious circle. It's a situation with no escape. If you get a chance to see the movie, it's an old movie. I think it's from the 70s, last century. Okay? Then I can consider execution time and performance in this relation. And essentially what I want to achieve speed up. This is my goal. That all the tricks that we are trying to look at and we are investigating have the goal to win performance. Then to get an execution time which is shorter than the one which is having the larger speed up, it's the better processor or the better platform. What is happening there? Something brilliant outside. No, you are looking there. Okay. Now, what does it mean, time? Time means a lot of things. Time is the time that you see as user for an application to complete, to finish. This is one sort of time. But this time is spent between the operating system, the application, the input-output requests. Then it's not only the execution of the application by itself, which is important. There are other things which do participate in the time, in the execution time. Now, in order to be able to get a real assessment of your processor, you have to look at the right parameters, and you have to somehow prune the things which are not really relevant. Let's say if I'm looking in the processor, input-output operations belong to another kind of workhorse. Then I should try to concentrate on the execution time of the application and not on the other components. Okay? Now do you know Unix? Okay, it's brilliant. It used to be a very nice operating system. Now we have it behind Linux, we have it behind Mac OS, but it's kind of hidden in a capsule. Then if you look in Unix and you ask for time, you get that kind of information. Okay? Then time may mean a lot of things. But you have to be sure that you compare the right time. Now, how do you compare? Come on, guys. Keep on coming, keep on pouring. But it's not yet 11 o'clock, and you are not late. You know, we have the academic quarter before starting the course, and we have the extra academic quarter after starting the course, right? Then, if I want to compare two processors, I have to use some kind of applications in order to evaluate their performance. Those are called benchmarks. As I mentioned last time, as a scientist, I would have loved to be able to do a demonstration like in mathematics, to take processor A, processor B, get some kind of mathematical module, do mathematical derivations, and end up with a conclusion which will say A is better than B. Unfortunately, this is not possible. And some people are happy, not me, but other people, most of the architects are happy to do things in this way. And they have a reason for that. You know, mathematics is a nice, elegant way to solve a problem. But in reality, things might be different. I would really appreciate if you don't eat during the classes. Not to mention that it's forbidden to eat according to the rules and regulations of the TU Delft. You cannot bring food here, coffee, things like that, right? Do you know that?
No, I haven't.
Okay. Then, now the question is what type of benchmarks to choose. Because you have to have a fair comparison, and the comparison and the results of the comparison will depend on the benchmark that you are choosing. And there are many, many benchmarks, and I will run through them in just a second. Now, first of all, we should have a kind of agreement on how we do the job. Then we need a kind of standardized approach. Because I may play my own game, and I will try to select things which are potentially advantageous for my processor, And you will try to get other kind of applications which are potentially advantageous for your processor, and then we don't have a fair comparison. Then that's the first part. The second part is that we can choose different kind of applications or different kind of benchmarks depending on what we want to demonstrate and on the application domain. And you see, you have here some kind of benchmarks, starting from real applications, going down to modified applications. Now, if I start with, the best solution would have been to get a real application. But that application might have a problem with portability, because it might work directly on your platform, and I may have to do some kind of tweaking in order to make it run on my platform. And then I may cheat, even though I'm not supposed to do that. But I have to, because otherwise it will not run. For that reason, actually what we do, we take the applications and we do a bit of kind of, engineering on them. We remove parts which do create problems with portability, and we take out things which are not relevant. Okay, now, those are benchmarks which are, kernels, toy benchmarks, synthetic benchmarks, and those are kind of not really utilized today. Today we have other kind of benchmarks which are the spec and other standardized benchmarks. But kernels are still of interest, because kernels will tell me about how effective my processor is on the part of the application which is executed the most. There is a kind of rule of thumb which is saying that most of the applications do spend 90% of the time in 10% of the code. Now, those 10% are the kernel. If I do good on the kernels, I do potentially good on the entire application. Okay, those are other things like, do you know what the third name of the Quicksort, sieve? Do you know what that is, the third name? Have you heard about that? Hmm? You know what a sieve is? The Greeks should know the name of the guy, at least. Hmm? You never heard about this sieve? Did you study mathematics in high school? No? Okay. Then you have homework to find out who Eratosthenes was and what is this sieve about. It's not about processing flour, okay? Even though you have a sieve also in the kitchen to filter the flour. You look at me like, never heard about. Have you ever been in a kitchen? Then in the kitchen you have a sieve. You may even filter the tea, but it's usually good for flour, or for maize flour and things like that. Eratosthenes was a smart guy who found a solution to a difficult problem by having that. But don't have to know, even though you have homework for next time. Hmm? You'll tell me next time who Eratosthenes was? But I'm surprised the Greeks, because there are some Greeks here. I don't see them from the... Okay, you are Greek, I remember you. It's quite strange it's Greek. How come that you have red hair? Because in the mentality of the Europeans, when you think about red hair, you look in the north. You know, the Vikings, Okay, let's return to the... There are also synthetic benchmarks, which means I'm taking instructions, I'm making a mixture of instructions in a program which does not make any sense, except that I'm exercising instructions in a certain proportion, and I'm going through all of them, and I'm doing more the instructions which are more relevant. There are a couple of those, dry stone, wet stone, which used to be very important in the past. Maybe you heard about Drystorm. No. Okay. Okay, now I take a benchmark, but one is not enough. I put more in a collection and I make a suite. Why do I need more? Because different benchmark has a different flavor. It's kind of stressing more one part of the processor or one aspect in the communication and things like that. And then we make a suite. And depending on what I want to, you are really like,
Sorry.
no, it's not allowed any longer. You are 1 minute past 11. No, don't get stressed. And depending on what I want, I may choose one of those. But the most famous one is the spec. The spec benchmarks are some benchmarks which are accepted by the computer architecture community for the evaluation of the general purpose processors. And if you do good on spec, everybody will say you're good. Then if I want to publish something, I made an invention on an architecture, and I want to publish it, what I have to do is I have to do simulations on spec benchmarks and to compare with the competition and show that I'm doing better. If I can show that, I'm in business. Everybody will say, you know, you have a good result, you'll be published. And that's important for your career if you are in academia, it's important for your grade if you are a student, it's very important for your graduation if you go for a PhD, it's important for the master thesis, because as I mentioned in the master thesis, essentially you have to come with some innovation. It was a ghost. It was Bull's ghost. Remember Mr. Bull? We are in his room. Okay. Now, the spec benchmarks did change in time. And the reason why they changed is because also the application changed. And there is a community, there is a kind of committee and an organization which is taking care of the evolution of those things. And from 89 to 2006, we had different kind of benchmark suites. And if you want to demonstrate something for today, you have to look in the latest one. You have to pay to get access to them. Now, if you are doing your master thesis in a group which is doing computer architecture research, they will have it. Is there any kind of rain in the room in your area? No? It's raining there in the corner? Are you? You have a head. Yep. No, you. Yeah, it's raining there or what?
It's not a hat for rain.
But for sun.
For sun.
Okay, there is very
But
hard.
there's no sun in here.
You can do whatever you want. I'm just a bit surprised when people have a hat inside the room. It's not exactly in my Bible book. Okay, now, you see, the advantage is, I don't really understand why this slide was put here, but it's an important slide which is telling you something about benchmarks also. Assuming that I have a processor, the processor is working together with a compiler. Unfortunately, it's very difficult to write the code directly in binary, even in assembly. Then we have to rely on a compiler. The compiler can do a good job or a bad job. Now, the compiler is effective sometime, but not on all benchmarks. Then we see here something like, you know, I have the same benchmarks, the same architecture, and I have two compilers. You see that the enhanced compiler, it's kind of not doing anything except for two benchmarks. Then that compiler has an optimization which can be taken advantage of in only two benchmarks. For the rest, the performance is the same. Now, this complicates a bit the comparison, because it's not only the processor, the architecture of the processor, who is playing in this comparison, but also the compiler. And in order to be fair, you have to try to do things in such a way that you are not perturbing the comparison, and your data you have to be as clean as possible. Now, this is an evolution of the spec benchmarks. They were kind of simple before. Now, today, you have a lot of things, you know, like even quantum chemistry, numerical, whatever, final, okay. All sorts of modern applications which do require a lot of computation are part of that. Now, you may run those applications and you get some numbers, but the numbers are different. Then you have to find a way to aggregate your results. And now I will make a small intermezzo. When you have the processor and you have the chip, you run those applications on a real implementation. Then you guys, you made the chip, I made the chip, we have competition, we make a setup, we run them, we collect the numbers, and we compare. But this is only one part of the benchmarking process. The benchmarking process, it's actually very useful whenever you design the architecture, when you define it. Because what you do is you make a simulator, an instruction set simulator, then you don't have real hardware, but you have a program which is running on your laptop or whatever. And that program, it's executing those applications, and your accuracy of simulation cannot be very low. You cannot go and simulate your processor executing this at SPICE level, you know, transistor level. Because 1 billion transistors, if you want to simulate that kind of programs, it will take forever. What you do is you make a cycle accurate simulation. And you say, I have this instruction set. This is the behavior of the instructions. Each instruction is taking that many cycles. This is in the architecture description of your processor. And then your simulator will execute some of those, all of those, and will say, you know, with this, you got that many cycles for program A, program B, program C. And you see now that there are some problems. And you identify the problems, you make some changes, and you do a new evaluation. This is without really making the implementation. Everything is behavioral. And this is, you know, a very strong tool in evaluating architectures before going into organization, realizations, and things like that. And you already understood that if I'm using the wrong benchmarks, I am getting bad, you know, it's garbage in, garbage out. If I'm optimizing an architecture which will be meant for signal processing on benchmarks which are, you know, general purpose benchmarks, I will not do a good job. And for that reason, you know, we have a part of the spec, we have benchmarks which are specific for different domains, like, you know, for graphics, for server, whatever. Now, I have those benchmarks, and I run simulations, and I have some numbers. Now, how should I understand the numbers? I have 3 computers here. I have 2 programs, and this is the execution time. What should I decide from this? Is it see better all the time? This will be a kind of misleading conclusion because there is a point which is missing in my comparison. I know the execution of each program on each computer, but there is something that I don't know. How often the programs are executed? Let's say if P2 is the one which is dominating, then for sure computer C is better. But if P1 is executing most of the time, maybe 99%, 99.99% of the time, A is better. Now, we need some kind of ways to aggregate the information. It's the same story that you have in logic design when you have two circuits, they have different delay in different area. And you would like to know which one is better. And you rely on area delay product. Sounds familiar? To some of you. To most of you? Okay. That is the same story here. And now, there are different ways to deal with that. We can say, okay, each program has a certain, weight in the execution. And if I know those weights, I can compute the weighted execution time. I can also normalize the execution time versus of one of the machines. There are different ways of doing it. They give you different things, and they also, some of them might not be available as information. If I have no clue on the distribution of the applications, this weighted thing I cannot apply. Now, this is an example on how I'm doing the weights. If P1 is 80% and P2 is 20%, then I can make the arithmetic mean, and I can make the weighted mean. And you see there is a difference in the effectiveness of computer A and B in those cases. If I know the weights, and for this case, still C is better. But if I distribute the weights in a different way, I may arrive to the conclusion that A is better. And I can also do things like that, like normalize the performance to one of the computers or the processors. And we have here normalization versus A, normalization versus B. Now, which one of those I'm choosing, how I'm playing this game will very much depend on the context of the comparison. And I can also use what is called the geometric mean. That one, it's a pi, it's a product. But I don't know why the PowerPoint is not willing to make it in a proper way. I try to change it, but then it's the square of the product of the sample. And you see, I'm applying this now again, normalized to A, normalized to B, and I see that still, computer C is better. But in this case, the differences in performance are very big. And I'm also not taking an aspect in here. I'm just looking at performance, execution time, but I'm not looking in the investment to get that. Because if one is to compare, to take, let's say, a Ferrari, which will cost a lot of money, and compare it with, I don't know, a Fiat Lux, right? Or a Fiat whatever, Panda, or a Fiat Panda, which is very small, right? The Fiat Panda will cost me a lot less money than the Ferrari. Then somehow, if I go a step further, I have to aggregate this comparison with data coming from the cost and from the energy. Now, there is a very interesting law here, which is Amdahl law, which is giving us an indication about what will happen when we speed up the execution of a part of an application. In general, what you do is you say, okay, this is the application, this is the execution time. I see that, for example, that part of the application, let's say, which is utilizing floating point units, is slow. I invest more hardware and I make it faster. Now, let's say I'm making twice as fast. the question is how much will be the implication over the entire application? Because I have my application, which is long, I do some tricks in hardware or in architecture, and I'm speeding up a fraction of the application. And now the question is, how much will be the overall speed up? That's the goal of that was the goal of Amdahl, to understand that. And he arrived to this conclusion. Then, if I make a speed up on a fraction of the application, let's say the new execution time will be 1 minus f, which is the part of the application which was not sped up, times the old execution time, plus the speed up of the fraction f times O. Then this is my formula. And if I want to make now the overall speed up, I will divide old over new, and this is what I get. Now, what do I see here? I would like to have a speed up applying to the entire application. Now, in order to get that in an intuitive way, I should be able to maximize f. And I will get a total speed up as whenever f is getting close to 1. Unfortunately, this is not possible in practice. And we have here an example which was exactly about floating point. Then I am making, floating point unit twice as fast because it was slow, but my application requires floating point operations only in 10% of the code. Applying Amdahl's law, what I get is that the overall speed up is actually almost 0. It's very little. And I spend a lot of hardware and energy in getting, the floating point going faster. Then my investment somehow was not correct for the application that I was looking at. From the other point of view, let us assume that my application was executing a lot of floating point, let's say 90%. Then the decision would have been good. Now, this is coming to, let's say, Gesundheit. God bless you, right? Gesundheit. The Americans. Do we have people from North America here? Yes, okay, then I should be careful not to make jokes about some people may feel offended, even though you should not. Where are you from?
Canada.
Canada, okay, it's different. Which Canada? There are 2 Canadas, actually 3 Canadas.
What do you mean, 3 Canadas? What do you mean, 3 Canadas?
It's the French-speaking one, is the English-speaking one, and it's the middle.
Okay, English.
You are from Vancouver?
No, well, Montreal, but I'm from the English part.
Okay. Then, okay, people in Canada, they speak supposedly at least 2 languages. Then they are not like the other Americans, which are monolingual. Okay, now, there are 2 conclusions in here, and they are very intuitive. Then you should put your money in the parts which count. Then whatever is the common core, you should try to speed up that, because that one will count. And the second one is like a corollary, if you want, which is saying that there is a kind of diminishing returns phenomenon. You put the money, your budget, in the most common part. You get a speed up. You still have some money. There is no way to improve on the common part. You invest them in some other part. The return on that investment is actually a lot smaller. Then there is no way to do an incremental investment with the same yield. Okay. Okay. Cool. Difficult or not? No? Okay. Now, in order to evaluate the CPU time, which is the important part for the evaluation of a processor, we have to look in 3 parameters. the instruction count, then how many instructions I'm executing. We have to look in the cycle time, which is also the frequency of the execution. Cycle time and frequency are very much related. And we have to look in what we call CPI, cycles per instruction. Then the number of instructions multiplied with the cycle time multiplied with the number of instructions, number of cycle per instructions will give me the CPU performance in terms of time. This now I can measure it in seconds or in milliseconds or in whatever. All terms do have the same kind of contribution. Then if I'm doing something good on one with 10%, the overall will do better in 10%. Now, the question is, how can I improve on those? And I can improve on different things at different levels of abstraction. If I look at the instruction count, I can improve it at the program level. Then if you write in a way which is more effective, you diminish the instruction count. I can improve it at compiler level, because the compiler can do smart things and undo the bad things that the programmer did. And you can also do that at the instruction set level. If you have instructions which are like RISC instructions, which are simple instructions, you need more instructions. If you have instructions which are like CISC instructions, complex instructions, you have less instructions. Now when you play with program and compiler, you reduce the instruction count, and by implication, you also reduce the cycle per instruction. It's not that you do that directly, but it's a consequence of diminishing the instruction count. Now, when you play with the instruction set and you make instructions more complex, you reduce the instructions and also you reduce the cycle per instructions. You can do that. And by implication, you can also diminish the cycle time. You might, but most of the time, it might increase. Because you push here, it pops there. And you can deal with cycle time and with CPI at the organization and technology level. Now, if you want to do a good game, you have to play in all the fields. Then the time when a solution could be applied successfully at one abstraction level only is gone. Now, in all the things, in all the games that we do, we start from top and we go down. If you want to do energy management, energy efficient computing, you have to start at the application level, because you can do wonders at the application level if you do good programming at the application level. The compiler can help you, the architecture can help you, the technology can help you, the organization can help you. In the organization of the processor, you may include things which are not relevant for the user, like, let's say, sleep mode transistors. And you put to sleep parts of the processor which are not utilized. If you are running an application which is integers only, you can detach the floating point units from power supply, and then they will not consume that much leakage. Okay, those are things which are not part of the architecture. You don't expose them to the user. You might, but you don't have to. You can include an instruction in your instruction set which is saying, now put to sleep that unit, and the program can control that. But most of the time what is happening is that the operating system is looking on what you do and is taking decisions. Okay. Now, in order to better understand the CPI, which is an important parameter for performance, you have to know the CPI per instruction But again, you have to know how often those instructions are utilized. And in the same way as we did with the weighted programs kind of thing, we can do for instructions. Come on. Then, this is an example on how I'm computing the average CPI for a processor. I have a processor, and essentially, in modern processors, I have three types of instructions. There are three classes. ALU, which are, the computing ones, the ones which are doing, the real work. Loads and stores, which are feeding the computation core and storing the results wherever I have to. And branches, which are controlling the execution flow. Typical, in a processor, you may have things like that. The ALU will take one cycle, load stores two, branch two. Now, assuming that I have a certain application, or based on many applications, I can obtain that kind of frequency. I'm saying that 50% of my instructions are ALUs, 20 are loads, store are 10, branch are 20, and based on that I obtain the weighted CPI, and then I do the average, and this is my average CPI for this processor, which is saying that on average, based on that distribution, I am spending 1.5 cycles per instruction, which means that 1/3 of the execution time is going on ALU, and the rest, 2/3 are distributed over the things like that. That kind of calculation can tell me something about the performance of the processor. And I do that before I do the implementation. Now, this will hold true whenever I can keep that story about cycles. If things are changing on cycles, things will change. And there is something more in here. I may have to sacrifice the frequency in order to keep that proportion, which might not be beneficial. Then just increase the cycle time. Do you know who is determining the cycle time of the processor?
The longest command.
The longest what?
Instruction command in the CPU.
The critical path in the implementation. You heard about the critical path? No? Come on, guys. You didn't have logic design? It's the longest path in a circuit. Okay? Now, most of the time the processor is pipelined. Then the longest stage in the pipeline will determine the frequency of the clock. And where is good to have that? Most of the time, the adder should be the one which determines the cycle time. There are some kind of rule of thumb. Addition takes 1 cycle. Multiplication, if you do it in the most effective way, it takes 2 cycles. If you are smart and you have in your processor a multiply and accumulate instruction, which usually takes as 2 instructions 3 cycles, you can do it in 2 cycles too. Division depends, may take more cycles. But somehow the frequency is determined by the adder. But in order to understand more on that, you have to see me in 3rd quarter on computer arithmetic. And then you'll get more insight on that. Now, in order to simplify things, most of the people, when they do an evaluation, they assume that only the CPI is relevant. Then when I'm comparing 2 architectures at high level, I'm saying I'm doing the calculation of the cycles per instruction as I did it in the previous slide, and then I compare only those. Because I'm assuming that that kind of changes are not changing the frequency and are not changing the instruction count. This is an assumption which may not hold true. At that level of abstraction, I can disregard the consequences of a small change in the frequency. If I go down to an organization and I'm starting implementing that, it may or may not have consequences. But as a first approximation, just the ratio between the CPI of the old and the new architecture will give me something about speed up. Okay, I think you have to know. Cannot keep you longer because you're complaining, right? I'll finish that.